So far, we are learning about spectral graph theory. The main task that we did was try to figure out the meanings of the eigenvalues in terms of, graph property. When we have a graph and it has some graph property, then we want to make a connection with these properties with the eigenvalues of the graph. Either it could be eigenvalue of the adjacency matrix of the graph or Laplacian matrix of the graph. But there are more things that we can do by considering this adjacency matrix and Laplacian matrix. So one of them is we can figure out the number of spanning trees. So this can be done considering linear independence or length of the matrix. When we have some matrix corresponding to the graph, then there we can consider length, or we can consider whether the columns are linearly independent or dependent. Those are also those are very important concepts in linear algebra. Then we can figure out the meaning of that in graph. Roughly speaking, linear dependency is related to cycles in graph. And in a similar spirit, linear independency is related to trees. The graphs without cycles are trees, and the collection of vectors which does not contain any linear dependency are the linear independent sets. So linearly independent sets and trees are related. Roughly speaking, consider an incidence graph. Incidence graph, what you have vertices here on the row, and you have edges in indexed. The columns are indexed with the edges. There, all the column vectors are specific. So if this is ij, this is 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. This is 1 on i's coordinate and j's coordinate, and the rest of them is 0. Okay? And in such a graph, if you have a cycle, E1, E2, E3, ek, and how are those vectors corresponding to those edges? So you have this is 1, 2, 3, 4, 5, just to make it easy to display. By ordering these vertices in this way, you have these vectors. And the last one is in this way. So what happens if we add them all together? There could be other vertices as well. So this is 1 to k. If you add them, then you have 2, 2, 2, 2, 2, 2, and 0, 0, 0, 0, 0. If we consider it as a characteristic 2, so if we just assume that 2 is same as 0, then this is 0 vector, giving the linear dependency among these set of wedges. But since it's more convenient if we work on the real number, we can instead of consider the incident matrix of directed graph. Meaning that each edge, you give an orientation in arbitrary way. if it is from U to V, then you can, say that instead of writing 1, 0 here, if this is from I to J, then you write so this is I, J, then you write plus I or minus what, plus 1 in minus 1 in each of the, let's keep it the other way. This is minus 1 and plus 1 if this is from I to J. So I's coordinate is negative 1 and J's coordinate is plus 1. In that way, it could be either plus minus, depending on our orientation, it could be minus plus or plus minus, minus plus or plus minus. So in this way, in that case, we take these edges and then we multiply either plus 1 or minus 1 and add them, then we get 0. So we get the linear dependency. So using these, we can relate the linear dependency and cycles in this instance graph of the oriented graph. So one of the concepts that's measuring whether the certain matrix has full rank or not. So full rank means that all the columns are linearly independent. The determinant is non-zero if this is full rank, otherwise it's 0. So using determinant, let's say here, roughly in order to compute the number of spanning tree, what do you have to do? You choose n minus 1 edges. And then if they are linearly independent, then it will correspond to the spanning tree. We didn't prove it, but based on what I just said, intuition is that. And we want to, in order to count the spanning tree, we want to count those choices of these n columns, which are linearly independent. And then for that, determinant is a useful tool. So as determinant is detecting the matrix with the full rank, and then the columns here are n minus 1. And in order to determine whether they are linearly independent or not, so this matrix you take is n by n minus 1. So which the number does not match. So one is the number of rows is one larger. So we delete one row and then we consider this. And then if this is full length, that corresponds to spanning tree. So that's the intuition. And we can use determinant to check whether that n minus 1 by n minus 1 matrix is indeed full length or not. So this actually, give us the following theorem. So if you make this intuition rigorous, then you can prove the following. So let's say you know L sub G is the Laplacian, and let's write the L sub I of G be the principal cofactor, which is the matrix obtained from the Laplacian by removing its ith row and ith column. With this definition, we can prove the following matrix T theorem. So the number of spanning trees of connected graph G on the vertex set greater than is what? It's the determinant of this principal covector. And this is actually equal to the 1 over n times all the eigenvalues on the non-zero eigenvalue. We know that this is connected graph, then lambda 1 is 0, and then rest of them are all non-zero for any I where this lambda 1, lambda 2, lambda n are the eigenvalues of LG. So we collect the following well-known fact, which is called the Binet cost formula. So if A and B are n by n and n by n matrix with a n being smaller than n, then we have the determinant of A, B is same as summation of all entries. So you choose M indexes, which forms the vertex, which forms the set F. And then you take the determinant of A and determinant of B, where this A bracket is the m by m matrix. And by splitting all columns of A not indexed by S, and similarly B bracket is the again m by m matrix obtained by splitting all rows of B which are not indexed by S. So this will be useful. So what can we do? Again, as I mentioned before, what we want to consider is that we give the orientation of the edges, and then we consider its instant. So we orient the edges of G and let P of I be the incidence matrix of this with I's row removed. So how the B of I look like? So we have everything here except I. Then we have E1, E2, all the edges of G. And if EJ is from B to W, the U to W, then what? This is -1 on U. This is +1 on W. Then what we get is that if we take this BI, n-1 by M, then it's completely, it's transpose. If you multiply it, then you get the Laplacian covector, I covector. So this is easy to see, because if you take, original incidence matrix transpose, then what do you get? You get that from U to B, so here UB entry that you consider U and V, then you and take for each HE from U to V. So if you consider that specific E, then the one of them here is like -1, here is +1. So let's write it this way. So if you have E, which is from U to V, then you have U here, and then you have V here, and then you have E, E. Okay. And the UV entry here is -1 if there is an H between U and V. Because in this case, so this coordinate is 1 and this coordinate is +1. And then they are exactly multiplied to yield this entry. So how does how does this matrix look like? So all the coordinates which correspond to the edges of G are -1. And then on the diagonal, what do you have? On the diagonal, you have that you consider U and U here. Then on U, you have -1 or +1. On the edges, you are incident with it. And then here it's same. And then you multiply it, and these are paired, and then add it. So you get the degree of the vertex. So at the end, you get the degree minus the adjacency metric, which is exactly the Laplacian. And then here, you can do the same thing with the I's law removed, and you get the principal cofactor here. And now, we can claim that what do we know? We have this Cauchy-Binet formula, determinant of this product. You can reduce it with the determinant of this. And then now we can prove that these terms are related to spanning tree. So that S is a set of n-1 edges of the edges of G. Then what do you have? Determinant of the BI, then you just take the columns corresponding to S. So this is either plus or -1 if S is the spanning tree, and 0 otherwise. So first, if S is not a spanning tree, then what? It contains a cycle. And by the observation before, those cycles correspond to 1 and -1, 1 and -1, 1 and -1. And then if you take them and then you multiply some of them -1 so that it's all consistent, and then you add them, then you get 0. Then what? The columns of these are linearly dependent. So the determinant is 0. If S is spanning tree, then what? We know that if it is a tree, you can order the vertices in the degeneracy ordering so that all the vertices have at most, usually one earlier neighbor. Then you can flip it so that every vertex has almost one later neighbor. Then, and one more thing is that for whichever vertex you take, you can make sure that it's the last vertex. And what? We can order the vertices. Say P1, P2, Pn, where the last one is the I. Such that each Pj has exactly one neighbor in rider index for each j in the first n minus 1. So this is the one that's removed from this B. So what? Now we permute the rows and columns of this in such a way that P1 to Pn minus 1 are in order. Let's say let Ej be the edge from this Bj to this. So you have a unique edge, unique such edge. So this is here. So we permute the rows column so that these are in order and E1 to Ej are in order. Then what do you have? You have a E1, E2, En, E1, E2, En minus 1, N minus 1 here. And then how does this look like? This stands from P1 to somewhere here. And E2 does not send any edges to P1. It's only sending, it's between P2 and some other vector, some other vertex here. And then E3 is between third vertex to the later vertex, and so on. So these diagonals are all 1. And this above part is all 0. This is lowest triangle. With diagonal all 1. I mean, technically all plus minus 1, sorry. So it could be plus 1, it could be minus 1, minus 1 plus 1, because we have oriented. So then its determinant is plus or minus 1. So this proves the claim. So now we have this claim, and with the Cauchy-Binet formula, or Binet-Cauchy formula, we can prove what we want. By using this Binet-Cauchy formula, what do you have? Determinant of Li, which is principal cofactor, is what? We take the determinant of, we choose S, which are the collection of n minus 1 edges, and you take the and for that you have E of I bracket S and its transpose, and then this determinant and this determinant are same, so you get the same summation, and then you get this is determinant square. And then this is what? This is 1 if and only if this S is a spanning tree. So this is the number of spanning trees. Okay. Okay. And furthermore, we can check that this equality also holds. Why? How did you obtain eigenvalue, you take the determinant, and then you take the I principal cofactor minus x minus a. Okay, let's just say the original Laplacian. So this is same as lambda 1 minus x times lambda 2 minus x times lambda n minus x. And then you solve the root of this polynomial, and then that's how you obtain this eigenvalue. Then here, what you know? You know that lambda 1 is 0, so you get that. Okay. Then what? We consider the coefficient C of the linear term. And C is what? Negative lambda 2 times lambda n. You multiply lambda 2, lambda 3, lambda n, and then you take negative, that's C. Okay, but what is it? So in this determinant, you have what? In this L, you have like T1 minus x, T2 minus x, Tn minus x on the diagonal, and then you have other things here. And then when you, what's the linear term? Linear term is that how you compute it. You take one of these, and then you delete, and then you take the determinant, and then you multiply. That's how you compute the determinant of this. So you take this, and then you take the, okay, let me say it again. You take all the possible like permutation, so that you choose the terms which have you choose the entries which contains exactly one from each row and exactly one from each column, and you compute the, okay, give me a moment. How do I say it? Yeah, so yeah, let me say it again. The determinant is that you consider all possible permutation, and then you take the percentage is sigma. Then you take the, for first row, you take the sigma I, sigma 1 entry, second row sigma 2 entry, and then you multiply them, and then you multiply the parity of this permutation, and you add them. In terms of that, you take this, and then you take the determinant of it, and then you multiply it, and then you do this. You keep adding this, then you get the determinant, and then in order to obtain the the linear term, you choose one, and then you forget that you don't consider the terms that you further multiply x, and then you take the determinant and then multiply, and you keep add them. Then you can see that this linear term is actually addition of n terms, and each of them are this principal cofactor. So, and yeah, so this is actually minus of n terms, and each of them are the same value of this principal cofactor. And from that, you can actually show that for whatever I you take, you know that its value is same. For different choice of I, this is also same. So you add them, then you get this n times the principal cofactor, then you get this equality. Okay. And in particular, if we try to compute the Laplacian of complete graph, then the Laplacian of complete graph you can check that this has eigenvalues 0, n, n, n. So n minus 1 copies of n and 1, 0. Then this shows that this kn contains what? N to the n minus 1 and divided by n, so n to the n minus 2 spanning tree. This is not counting the isomorphism graph, so some of them can be isomorphic, but in Kn, you have this vertex labeled. Then this tree and this tree are different trees, even though they are isomorphic. And if you count them all, then you get this number. So we used this in one of the previous sections when we deal with the random graph. We were determining the threshold probability for connectedness. We use this fact. Anyway, so this is one example of how we use the fact that the cycle corresponds to the dependency in matrix, and then we use them to get a formula for spanning using determinant of the matrix or the eigenvalues of the Laplacian matrix. Okay, so that's it. So that concludes the this semester course in the introduction of the graph theory. Yeah, thank you for listening. I hope this was informative lecture for you. And I also apologize some of the explanation was a bit floppy and maybe it was a bit too fast in some lectures. But overall, I hope that you get some ideas on what we learn in graph theory, and I also hope that this was interesting to you and beneficial for you. Thank you. Okay, thank you.